Hi everyone, my name is Ria and I'm from the University of Sheffield. So, have you ever wondered why moms are always the best at finding any item in the house? Do you think it's because they know everything or they have better exploitation strategies or because they are lucky? Well, I'm going to say it's because they know how to exploit the knowledge they already have about the house. And in most cases, they spend time exploring the house while cleaning or tidying up. This is relevant to reinforcement learning because reinforcement learning is a framework where an agent tries to find the optimal policy through interacting with the environment. In this case, the agent explores the environment to gain knowledge about it and then uses it to act optimally. So, essentially, exploration and exploitation are key to finding the optimal policy. Some of the open questions in RL exploration are how to determine whether an agent is exploring efficiently, and how can one evaluate various exploration methods quantitatively? These questions have been the center of discussion at an ICML workshop since 2018. Current solutions are regret or performance, and the number of updates to convergence. While these have significance and are valuable in their own rights, they don't quite precisely capture exploration efficiency. In fact, they're analogous to a scenario where you're trying to lose or gain weight and measure what that weight is, but you don't have the ability to measure that weight directly. So you look, so what you do is look at your running speed, and based on that, you infer your weight or mass. For example, I ran faster today, and it means I must have lost like 2 kilograms. Even though mass does contribute to how fast you run, there are numerous factors that are involved, such as what you ate, the quality of your sleep, and how long you've been practicing, and etc. So you can't just lump it up and say because of your running speed, definitely this is how much weight you have lost. That is the reason why it is essential that we find a way to directly and precisely measure exploration efficiency. So what we did is define what is an exploration process, which is an interplay between exploration, exploitation, plus the learning strategy of the algorithm. This influences how your policy model updates from one policy to the next as it learns. With this defined, we want to be able to compare different exploratory processes using a method that is task agnostic and algorithm agnostic. And we want to capture exploration efficiency and be able to observe various characteristics of these exploratory processes. So one of the things that we realized was that we can tackle this by representing our policies as probability distributions over the state action space. And these distributions are called occupancy measures. The beauty about occupancy measures is that they have a one-to-one relationship with stationary Markovian policies. And we know that in reinforcement learning, as trading progresses, there is a sequence of evolving policies. Typically, you begin at some random initial policy, and as time goes by, every update, with every update, you reach a final optimal policy or some near optimal policy. But this produces a corresponding sequence of occupancy measures because of the one-to-one relationship. And because now we have property distributions, we can build an occupancy measure space. This is a space of property distributions. This allows us to use tools from information geometry. However, these tools rely on this theorem that we have proved. That is, if your policies are smoothly parameterized, then you have a differentiable manifold. And with this, we have the ability to apply information geometry tools. Just an idea of what you're looking at here in figure 1. This space or manifold is not necessarily two-dimensional, but it is multidimensional. But for illustration purposes, we made it look two-dimensional. And what we have here is that as your reinforcement learning algorithm learns, it moves from pi naught to pi 1. Then it follows this path that we call C all the way to pi star. However, we know from imitation learning that when you already have a data set from an aspect, you can simply utilize supervised learning. And with that, you will be moving directly from pi naught to pi star, basically following this shortest path that we call L. The other thing, the other thing is that if you look at figure 2, you can see that this line is solid as well. It's also the C path. But however, we want to highlight two items here. One is the distance from pi, 80 pi, to the optimal pi star, right? And we call this the distance to optimal. And the other one is the distance between consecutive policy updates, which is pi 1 to pi 2 to pi n. And we call this stepwise distance. We use x and y to represent these distances because it helps us visualize what is happening. Another point is that we decided to endow this space with a Wasserstein metric. But nevertheless, you can also use other information geometry metrics on this space. To compute the Wasserstein distance, we need a ground metric on the state action space. But states and actions have different metrics or can have different metrics. We overcome this by mapping actions to distributions over the state space using a method called the optimal transport dataset distance. This uses a nested Wasserstein distance to compare actions over the state space, then essentially have both states and actions grounded on the state space. And this makes the ground metric of the state action space the default metric of the state space. So what we have here is the visualization of policy trajectories of three selected algorithms on a simple 5x5 2D grid wall problem. The vertical axis shows the number of updates from 0 all the way until convergence, as is shown here. While the other axes are stepwise distance and distance to optimal. We can see that over time, as the algorithm learns, it goes to 0, 0 because it have reached the optimal policy. We notice that comparing these two extremities, we see that the UCRL2 is more erratic in how it transitions or updates from one policy to the next policy. Compared to the soft actor critique, which is reluctant to change policies and thus has a smoother transition when it moves from one policy to the next policy. Then you have something in the middle, like the PSRL, which tapers over time. It begins with like high variance, but then over time the variance reduces. It gradually reduces until it reaches convergence. This gives us an insight of how these algorithms evolve over time or evolve as they learn. Also, you can tell which algorithms are more stable as they reach the optimal policy. Noting that some algorithms will reach the optimal policy, then cope and go past it if training continues without terminating upon reaching the optimal policy. And you can see that with UCL2, that it does look a bit unstable or less stable compared to the other two algorithms. And yet it's true. In reality, if you continue training the UCRL2, it will reach the optimal policy. But if training continues, then it will go past the optimal policy compared to the other ones, which will settle at the optimal policy. So we propose two forms of exploration efficiencies. The first one is about how we can compare this path C with this path L and find the ratio, which we call the effort of sequential learning or is ESL, right? Essentially, this is effectively C divided by L. The second one is the optimal movement ratio, OMR, which is the portion of useful updates to convergence. In this case, if you look at this diagram, you can see that if we move from pi naught to pi 1, I'm essentially increasing my distance to optimal, right? Because my x1 is greater than my x naught. So therefore, we consider that this update, we consider it as being wasteful because it didn't help us to get closer to the optimal policy. But however, if we move from pi 1 to pi 2, we realize that the distance to optimal has been reduced, right? Because my x2 is less than my x1. So therefore, we consider this step to be useful. So in order to calculate the OMR, we collect a set of all useful policy updates and divide it by the total path, which is path C, and this gives us OMR, which is basically the proportion of useful updates. In our experimental results, we show ESL, OMR, and the number of updates. And we see that soft actor critique is standing out as having a better exploration strategy compared to the other ones. But one thing to underscore or to take note of is the number of updates. We can observe that PSRL has the best number of updates. And this goes to show the dissociation that I mentioned earlier at the beginning, that the number of updates tells us about the overall algorithm, but does not necessarily explain much about the exploration efficiency of the algorithm, while ESL and OMR capture it more. Another interesting thing is that even though soft-actor critique is known as the state of the art, it only has about 60% of useful updates. So that tells us how much we as RL researchers need to find algorithms that have higher useful updates. These results are for a 2D grid world with deterministic density rewards. Furthermore, we came up with some theorems to capture one, the error bounds for estimating the Wasserstein using datasets, and two, as well, we proved that our approach is related to regrets for MDPs with Lipschitz rewards. For such MDPs, regret is upper bounded by the sum of distances to optima. And now, in a case where you don't have access to the optimal policy, or your algorithms don't update and they do not reach the optimal policy. And this is the case where regret essentially breaks down. We found a nice relationship where we said eta sub is when you compute ESL, where pi n, the final policy, is not the optimal policy, versus pi n when is the optimal policy. And these have the relationship that we show here. Also, in practice, we realize that even though the magnitude of ESL and ESL sub don't have much of a correlation, but in terms of ranking, they give us the same ranking, which is useful for relative comparison of algorithms, where you can say whenever you don't have access to ESL, you can use ESL sub to tell which algorithm has a better exploration scheme. In this table, we use a stochastic environment for illustration. So key takeaways about our work are, we can see that being able to see or visualize the policy trajectory in the occupancy measure space helps us to observe how the algorithm approaches the optimal policy. As well, we saw how ESL and OMR can capture the efficiencies of these exploratory processes. And the number of updates contains little information about how the policy evolves compared to the quantities we proposed. And another thing to add, ESL and ESL sub can provide the same efficiency ranking, which is useful for comparing algorithms that did not necessarily converge to the optimal policy. Thank you.